In this video, we're going to continue to investigate the linearity properties of the definite integral. So we're going to start by letting h of x be equal to c times f of x for c being some constant. And our question is, what is the connection between the definite integral from a to b of h of x dx and the definite integral from a to b of f of x dx. In other words, what we're really asking is, how are the areas underneath the h curve and the f curve related to each other? Well, to answer that question, what we really need to do is we need to look at the connection between the graph of y is equal to h of x and the graph of y is equal to f of x. And that is something that we've known since a high school algebra class. So again, what I want to do is I want to start by thinking about what the graphs are. So if h of x is equal to c times f of x, then we know that the graph y is equal to h of x is a vertical stretch of y is equal to f of x by a factor of c. Now, some things that I want to kind of verbally say without trying to draw too many pictures. It turns out that if c is smaller than 1 in its absolute value, that stretch is really a squash. If c is negative, we have a flip over the x-axis as well as a stretch or a squash. For drawing the picture, we're going to stick with a picture where, so our picture is going to be where our c value is strictly bigger than 1. And I kind of want to start by trying to draw a picture. And I want to keep things fairly simple because it's not the easiest picture for me to draw. So let's get a better set of axes in here. There's an x and a y axis. And I'm going to have my f function be something pretty simple. It's just going to look kind of like a parabola. So this is y is equal to f of x. Now, if c is bigger than 1, this is going to stretch this part of the curve in a vertical direction, and it's going to stretch this part of the curve and this part of the curve in a negative direction. And of course, 0 times anything is 0, so our new curve is going to go through those same roots. So let's see if we can graph this in a different color. Let's pick this color. So I know that I'm going to be going through, green is, that green is. So I'm going to be going through these 2 points. And I'm going to basically be kind of going like this. And if I fatten that up and I fatten this up, that's a good enough picture for a picture by hand. Let's see, I might be able to get this side just a little bit better, and so let's clean my picture up that way. Now, this new picture is y is equal to c times f of x. And the idea here is that no matter what x value I pick, if this is f of x, then this is c times f of x. Now, I want to get the definite integral stuff in there, so let's make this particular x value a and this particular one over here b. And so what I now want to do is I want to talk about what the integral for h is and what the integral for f is. So let me go back to yellow. The integral between a and b of f of x dx is what I'm going to call a yellow area. And the yellow area is simply this area. So it's bounded by y is equal to f of x. Now we have this kind of bright blue color, And I'm going to think about the integral from a to b of h of x dx. That's the area under the same over the same interval, but going all the way up to the h curve. So that is this blue area. Now, what I want to think about is that I know something about how to interpret the notation here. The h here is the height of that blue area. The dx is telling me that I'm sweeping the blue area out in the direction of h. So what I want to do is I want to really look hard at the height of the blue area. H of x is the height of the blue area. But now I want to give myself a nice, big, fat, clear set of what that height is. By the formula, that height is just c times f of x. And so when we are looking at the h of x times d of x, that height times width, and let me clean up my arithmetic here, or rather my handwriting here. So when we're looking at the height times width for the blue area, that is going to be equal to, well, the h of x is c times f of x times that dx. But multiplication is commutative, and so is associative. So I can regroup this, and I can get this written as c times f of x times a dx. And now what I want to do is I want to think long and hard about what this is. That f is the height of the yellow area, and that dx is the width of the yellow area. So gee, if the blue area is the blue height times the blue width, and the blue height times the blue width is c times the yellow height times the yellow width, it's reasonable to expect that our blue area is going to be equal to c times the yellow area. And that's because up here, our height times width of the blue area is c times the height times width of the yellow area. But now it's just a matter of putting the integral signs back in. So we remember that the blue area was nothing more than the integral between a and b of h of x dx. And let's see, that yellow area was nothing more than the integral between a and b of f of x dx. And the final thing that we need to do is we need to recall that h of x was equal to c times f of x. That's what made all of this stuff up here work. And because of this, we can say that we have the following rule. The integral from a to b, well, h of x is just c times f of x. So the integral from a to b of c times f of x, where the c is inside the integral, is equal to c times the integral from a to b of f of x dx. And this particular rule is called the second linearity property of the definite integral. And it's important to understand that we can read this particular fact as follows, that if we have a definite integral of c times a function, we can pull the c outside the integral sign. In other words, that c can go back and forth across the integral sign. This is similar to how derivatives work.